It would appear that the calculus has finally caught up with us in physics. Calculate the force due to water pressure exerted on a 1 meter by 3 meter aquarium viewing window whose top edge is 1 meter below the water surface. Many problems in your undergraduate physics career are going to be approached in the manner I'm about to describe. So check it out. What I have to do is what I've drawn here is a little thing I'm going to overlay onto my picture of the aquarium. It's a differential area of height dy. I'm talking about the surface area of the glass, and I'm thinking about moving it up and down here. And the reason I'm doing this is because I want to imagine it, for one thing, at the very top here, the very top of the glass. And we want to ask ourselves, what is the force on just this purple area that I've laid out here? Well, I know that it's due to exactly 1 meter's worth of water sitting on top of it. As I move it down, my imaginary subdivision of this glass, and I move it all the way down to the bottom, what I conclude is that at the bottom, the force on this differential area is, well, it's due to a whole 2 meters, all the water bearing down on this little area here. And what we're going to do is we're going to take this area, or rather the force on this area plus the force on this area, this area, this area, this area, blah, 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 all the way down to the bottom and sum them all up. And we're going to form an integral. And then we're going to solve the integral, and then we're going to get an answer. It's actually not as bad as it sounds, but it can be a little bit daunting on you the first time you encounter something like this. Wherever my differential area happens to be, I'm going to say that there is y meters of water above it, and that y meters is going to contribute to the force on that area. Okay, so if the differential area is up here at the top, then there is 1 meter, y equals 1. And if it's all the way at the bottom, then there is 2 meters of water bearing down on us, and y equals 2. All that being said, let me start my calculation with the most basic of fluid formulas. Pressure equals force over area. And I'm interested in force, so I'm going to rearrange this. I'm going to get force equals pressure times area. But I need an expression for differential force. For this guy right here, the force just on this tiny little slab, I guess, of glass. So I'm going to change this expression a little bit. I'm going to say dF equals P dA. And now I'm going to replace these abstract symbols with some things that I know. See, pressure, that is density GH. When I say H, I mean literally the height of fluid, or in this case, water above it. And dA, well, my A would normally be length times width. I'm talking about the area, literally, of my glass pane here. Normally it would be length times height, rather, in this case. But I'm talking about a differential area, which has all of the length, but only dy's worth of height. So if I clean this up a little bit, I'm going to change one thing. I'm going to get PG, but instead of H, what I'm going to do is I'm going to say Y. This is the general form, PGH, for a certain height of water above the area of interest, but now I'm going to say Y because that's the way I laid it out in my diagram. My differential area has Y meters worth of water above it, like I said before. L, D, Y. And I don't know if you can see where we're getting at here, but P, G, L, Y, D, Y is equal to DF. And of course, remember what I said before, we're going to add all of my differential areas together as I work at this layer, that layer, that layer, that layer, that layer, and that layer. Well, I'm going to have an integral. Integral from y equals 1 meter up here, where there's 1 meter of water above us, all the way to y equals 2 down here, where there's 2 meters of water above us, of P, G, L, Y, D, Y. PGL are all constants: the density of water, acceleration due to gravity, and the length of the tank, so I can pull them out of the integral. PGL, integral from 1 to 2 of y dy. And finally, we perform the integral. We get PGL times 1/2 y squared, which is evaluated from y equals 1 to y equals 2. And we're getting out of that, at the end of the day, 1/2 times 1,000 for density of water, times 9.8, times 3, which is the length of the tank. Now times 2 squared minus 1 squared, which should come out to about 44,000 newtons on my entire pane of glass.